Diagnosing and treating disease relies on manipulating invisible subatomic particles. Clinical practice requires aiming high-energy photons through a living patient to visualize internal anatomy. This requires a mastery of the architecture of the atom. This diagram compares the patient in a scanner with the microscopic Bohr atomic model. A technologist cannot control a force they do not understand. The historical evolution of atomic physics records how these forces were identified and measured. Mapping the internal pieces of the atom was an evidentiary process of isolating specific variables. These historical models provide the mechanical logic for every instrument on the clinical floor today. In 1803, John Dalton defined the atom as the smallest indestructible unit of matter. In this model, the inside of the atom is empty, containing no smaller subparticles. If atoms were truly indestructible, radiation could not strip away pieces to create ions, and X-ray imaging would be physically impossible. This model was challenged by applying high voltage to a vacuum tube, which produced a glowing cathode ray. When an electric field is applied, the beam bends toward the positive plate. These negatively charged fragments were identified as electrons, proving the atom has removable pieces. Because atoms are electrically neutral, discovering a negative piece required a positive counterbalance. Thomson proposed a model of negative electrons scattered through a positive soup. This provides the mechanism for ionization. When radiation interacts with human tissue, it targets these specific atomic components. Ejecting these particles from the atom is the exact process that creates radiation dose in human tissue. Clinical machinery requires the electron's exact mass, derived by combining its charge with the known charge-to-mass ratio. The mass is 9.1 times 10 to the negative 31 kilograms, essentially zero. Being so incredibly light allows standard clinical voltages to accelerate them to near light speed. Thomson's discovery of the removable electron and its negligible mass established the physics that makes creating X-rays and biological ionization possible. Ernest Rutherford tested the Plum Pudding model by firing heavy, positive alpha particles at a thin sheet of gold foil. The expectation was that these heavy projectiles would punch straight through the thinly spread positive charge. Instead, while most particles passed through, some deflected at extreme angles. The data showed the vast majority passed straight through, while a minuscule number bounced directly back toward the source. This established two new rules. The atom has an incredibly dense core and is composed mostly of empty space. This atomic void determines how high-energy electromagnetic radiation moves through the body. This empty space is why transmission imaging is possible. High-energy photons pass through a human patient without striking a nucleus. The resulting image is a map of interactions with electron clouds, rather than the nuclei themselves. Without Rutherford's proof of the atomic void, creating a shadow map of internal anatomy like this would be mathematically impossible. Rutherford's model had a flaw. Classical physics dictates that an orbiting electron is accelerating, which means it should emit continuous radiation. This loss of energy would cause the orbital radius to shrink. Under classical rules, atoms would self-destruct in a fraction of a second. The quantum solution is that radiation energy is not a continuous dial. It operates in distinct mathematical steps. When an electron drops from an excited state to a lower orbit, it releases the specific energy difference between those two levels. That energy manifests as a photon of a precise, measurable wavelength. This discrete jump is the source of characteristic radiation. Adjusting the kVp on an X-ray tube allows us to manipulate these transitions. The specific energies selected on a clinical console are the macroscopic result of these transitions. This equation is used to calculate X-ray wavelengths based on the console settings. By selecting a kVp value, a technologist is directly applying these quantum transition equations to control patient dose. These atomic principles determine the operational limits of diagnostic machinery. Structural imaging, like X-ray and CT, are exogenous modalities, where the radiation source is outside the patient. These rely on transmission mapping and electron cloud interactions. Functional imaging, like SPECT and PET, are endogenous modalities, where the source is inside the patient. A radiopharmaceutical combines a radioactive isotope with a biological targeting molecule. The isotope provides the energy signal, while the molecule targets specific tissue physiology. In this modality, the radiation is not shot through the patient. The patient becomes the emitter. Every nuclear medicine modality acts as a detector of subatomic energy transitions. Imaging technology takes these microscopic events and compounds them into a macroscopic heat map. Capturing these invisible emissions requires massive electronic arrays, calibrated to atomic precision. Clinical mastery depends on understanding these atomic mechanics well enough to harness the invisible, manipulate energy safely, and guide life-saving diagnostics.